Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have discussed a few important relationships relating some functions, important functions and their Fourier transforms, and we also looked at some of the important properties of Fourier transform, which we are going to use very shortly. Now, before we proceed, just one tiny piece of reference that we need to just make it proper. So, when we derived this particular relationship, there should be a negative sign, because as we take this up, here it is minus j omega, so there should be a negative sign over here, there should be a negative sign over here. So, as limit a tends to 0, this is 0, and you have minus 2 j omega upon omega squared. So, if you would multiply by j on the numerator and denominator, you are going to get a j in the denominator and a minus 1. So, that will be 2, and omega and omega squared would reduce to omega in the denominator, and here again back to you would multiply a j on the numerator and denominator. So, that will result here, because you have 2 by j 2 pi f. So, this 2 and this 2 cancels out. I again multiply a j in the denominator numerator, you are going to get a minus sign here. So, that minus sign and this j translates over here. So, that brings us that makes things sets things proper in our relationships. Now, we will use the relationships that we have derived in the previous lecture to look at signals that we are going to encounter for proper representation of signals for digital communication system. So, now we are interested in representation of band pass signals. So, we are slowly getting into communication systems. Once we are okay with this few expressions that we set up, then we will simply move ahead with those particular things. So, now we consider, let this be the f axis and let this be the mod of s of f. So, if we are looking at a signal which is narrow band, so that means it is centered around the carrier. So, beyond the carrier there is no signal, and if it is a sideband, it would look like this. So, we would call this, let us say, f c as the center frequency, and we are going to have something like this here, as well on this side. This is minus f c. So, s of t is a real valued signal with us, and we have seen that for real valued it is even symmetric, that we have seen in the previous lecture, and that is the representation over here that we have. So, we have also said that if s is real valued, then we can use only the positive set of frequencies to represent s of t, because the magnitude is even function, and if you are going to look at the phase, it is odd function. So, you can reconstruct the signal only with the positive set of frequencies. So, that means the positive. So, you have to reconstruct. So, if you have to construct the signal, you can use only the positive frequencies, that is sufficient. So, if that is so, we could write that s plus of f, indicating the signal with the positive set of frequencies, as 2 u of f times s of f. U is the unit step, SF is SF, and 2 is a normalizing constant. Other justification could be, since we are using half of the signal, we have to increase the signal strength. So, we are using 2 over here, and of course, we have the relationship that s of f is related to s of t, s of f is related to s of t via the Fourier relationship. This is the inverse Fourier, this is the Fourier transform, this relationship. So, we need to look at what is S plus of t. S plus of t we obtain by taking the inverse Fourier of S plus of f. So, to obtain that, we take integral minus infinity to infinity S plus of f e to the power of j 2 pi f t df. So, if we have S plus of f, we have to replace this by the same term. So, we are going to have 2 u of f times S of f and e to the power of j 2 pi f t df integral minus infinity to infinity. So, we could also say that since we are doing the inverse Fourier of this, it is the inverse Fourier of this function. So, that means we are saying we are doing inverse Fourier of S plus of f. So, or we could write inverse Fourier of 2 u of f times S of f. If so, we have a convolution, this is a constant, so constant does not affect. So, we have inverse Fourier of u of f convolved with inverse Fourier. So, you can keep the 2 of S of f, right, and we have actually done this in the previous discussion when we are doing so we had established this relationship. That is what we are going to use over here. That is why we did that. So, we are going to use delta t plus j upon pi t. So, we had a 2 and there also we had a 2, because 2 u of s is equal to 1 plus sine of f convolved with inverse Fourier of S f is S of t. So, we could write S plus of t by this relationship. So, moving forward, if we see what is delta convolved with this function, it is basically the same. So, it is S of t plus j upon pi t convolved with S of t. So, we could say that let us consider this as represented by S of t plus S cap of t, where you can say S cap of t is 1 upon pi t convolved plus j S cap of t convolved with S of t, that you could write as 1 upon pi, because pi is away as a constant, minus infinity to infinity S of tau t minus tau d tau. So, what we can say from here is that S cap of t is the output of a filter whose impulse response is given by h of t, which is equal to 1 upon pi t for t ranging from minus infinity to infinity. Such a filter that we have is known as a Hilbert transform. And you could recall from our earlier discussions, as we just made, this would help us. This is 1 upon f. So, it would hint where it has something to do with u of f, it has something to do with the sine function, because we were doing the inverse Fourier of, we are doing the Fourier transform of sine function, and when we did that we arrived at an expression which had 1 upon f. So, 1 upon pi f rather. So, similar thing is what we are going to encounter here, and here as well what you can see is this delta function remains as it is, and when we take this sine we have 1 upon pi t. So, this gives us a hint that when we are dealing with this 1 upon pi t, there is something to do with the sine function that will be there in the Fourier domain, or the Fourier transform relationship would be like that. So, we can state using our knowledge that h of f is equal to the Fourier transform of h t, that is 1 upon pi minus infinity to infinity 1 by t e to the power of minus j 2 pi f t dt. So, basically we are taking the Fourier transform of 1 by t. So, definitely this will be the sine function, and this you could say it is minus j, as we had seen before for f greater than 0, because there was a j involved. If you would recall this again, we had this j involved, right, and we started off with this function. So, if you see carefully this particular part, we had a j involved there. So, that will help us. So, equals to minus j for f greater than 0, it is 0 for f equals to 0, and it is j for f less than 0, and h of f mod value is equal to 1, and phi of f is equal to minus pi by 2 for f greater than 0 and pi by 2 for f less than 0. So, this is the relationship that would help us. So, if we have this, we can move forward and we can say that we are interested in the last expression that we have here. We have s plus of t. So, we would be interested in writing this particular expression. Yeah, here we have with us, this is the relationship that we were working on. This is the last term that we are trying to explore, and simply we have expanded here that this s cap of t is the Hilbert transform, which is given by this relationship of a filter where h of f is minus j for f greater than 0, j for f less than 0, and phase is given by minus pi by 2 and pi by 2 for different conditions of f, whether it is positive or negative values. It is a phase rotation, you can say. So, what we now have with us is this s plus of t. S plus of t is also called the analytical signal, or the pre-envelope. So, we could say that s plus of f that we have seen could be translated to baseband. You would like to translate to baseband, and you would represent it by S L of f, that is the low pass equivalent of the positive set of frequencies of S f. That is what we are talking about. So, we could write S L of f is equal to S plus of f plus f c. This is nothing but the frequency translation. So, if you would put f is equal to f c, we are going to get S L of 0, right. So, if f is equal to f c, if f is equal to minus f c, you are going to get s plus of 0, and so on and so forth. So, if you put f equals to 0, if I am going to put f equals to 0, I am going to get S L at 0 is equal to s plus at f c, and S L at, let us say, plus some delta is equal to s plus f c plus delta, and so on. So, basically if we go by our picture here, we are talking about bringing this spectrum here, right. We are talking about bringing the spectrum here as given by this relationship, and if you put SL of sum minus delta, where delta is a positive quantity, you are going to get S plus of FC minus delta. So, again if we look at this image, then things will be clear as to what is meant by SL of f. It is basically bringing it down here, and accordingly we have used this notation L to represent low pass equivalent, right. That is an important relationship. Okay. So, yeah, so that is what is S plus of SL of f. So, that means we could write S, if we have this thing, we could say that SL of t, because finally we are represented in the low pass, interested in low pass equivalent of the time domain signal. This we obtain by getting the inverse Fourier of SL of f. So, that would mean that we are going to get S plus of t inverse Fourier of this, but there is a scaling, and that scaling would mean e to the power of minus j 2 pi f c t. So, this is also by inverse Fourier. S plus would relate to this thing, as well as this would lead to scaling. We have already seen such relationships here. No, we did not give it, but of course, that is not a complicated one. Let me see if we have not given it, but it is evident from earlier expressions that we have looked at. So, this is the inverse Fourier relationship, it is a frequency scaling operation, as well as this is the corresponding time domain signal. So, once we have this, now we can get back to our expression of S plus of t. So, S plus of t is this relationship, right, that we have over here. So, we could simply say this is equal to S of t. Let's see this. I don't know if it's visible. It's probably not visible. Okay, S of t plus j S cap of t e to the power of minus j 2 pi f c t. Simply we have replaced S plus of t, this expression, into this expression over here, and we have got this expression. So, what we can see here is that S L of t is in general complex. It is a complex signal in general, and then you could write S L of t as x of t plus j y of t. If this is so, then you could equate the terms, that we would have x of t plus j y of t. If I would take this exponential on this side, e to the power of j 2 pi f t is equal to S of t plus j s cap of t, right. And then you can expand this, you are going to get this as cos 2 pi f c t plus j sin 2 pi f c t, and you have this term, you are going to get x cos 2 pi f c t minus y sin 2 pi f c t, because j and j gives a minus sign. So, we will equate this real part to the real part. So, you can get S of t is equal to x of t cos 2 pi f c t minus y of t sin 2 pi f c t. And if we look at the imaginary term, y cos 2 pi f c t with a j and x sin 2 pi f c t with a j, and we can equate with this term. So, we are going to get S cap of t is equal to x of t sin 2 pi f c t plus y x with sin and y with cos y of t cos 2 pi f c t. So, what you are seeing is that with the Hilbert transform, it is the 90-degree phase shifted version of S t, that is what we are getting over here. Plus, what we see is that S of t which we said is the real valued signal which goes out, is of this form, where SL of t is of this form. So, that means we can also write that S of t is equal to real part of, from this we can write real part of x of t plus j y of t times e to the power of j 2 pi f c t. So, the real part of this is a cosinusoid. If I only had x of t, what I would have got is x cos 2 pi f c t, which you have studied in analog communications. And here we have a signal form where we have a signal which is the baseband signal without carrier, up converted with a carrier, and the baseband part on the imaginary axis up converted with this. So, this is another important representation of the passband signal S t in terms of its low pass equivalent, and you could also write this as real part of S L of t e to the power of j 2 pi f c t, which is a very desired form. So, these are some of the desired forms which relates the passband signal to its low pass equivalent. So, that means, if I have a low pass equivalent signal, then I could relate to the passband through this, and we have arrived at a formal method of representation of the baseband signal, of the passband signal from its equivalent or its equivalent low pass representation from its passband, starting at a point where we said let S t be a real valued signal, and we said earlier, based on our Fourier relationships which we had established here, since we said that for real valued signal only positive set of frequencies contain the complete information. So, you said that let us take only the positive set of frequencies and represent it by S plus of f, where these are the Fourier relationships, and we then went to the time domain version, which we call the analytical signal, and we represented S plus of f as S f times u of f times 2 because we are taking only half the signal power. So, we need to take twice that to normalize it, and when we derived it, we had this we wanted to take the inverse Fourier of S plus of f, that is what we did over here, but we broke it down into factors. This factor we had derived earlier, this we simply write it as S of t, as in here, right. So, we found that it is S t plus j times some convolution with S of t, which we write as the filter known as the Hilbert transform with the impulse response 1 upon t, which we described. And then we said that S plus of t could be represented as S t plus j S cap of t, and we have slowly realized what is S cap of t through a few relationships as given in this expression. One could also represent S L of t as A of t e to the power of j theta t. So, if you do this, in that case one could represent in this case one could represent one could say A t, well known result, is equal to square root of x squared t plus y squared t, and theta t is equal to tan inverse of y t upon x t. So, one could write S t going by these earlier relationships as real part of S L of t e to the power of j 2 pi f c t, which we would now write it as A t e to the power of j theta t e to the power of j 2 pi f c t, which you could write it as A of t times cos 2 pi f c t plus theta t. So, these few expressions as we have over here, we can mark this as A, B, C and D are some of the important relationships that we require in representing the low pass equivalent form for a band pass signal. And with these representations, we can now go ahead and study communication systems, because whenever we will be representing signal, we will be doing it in terms of low pass equivalent form, and the reasons will be even more clear in a few lectures when we will be able to establish that you could study all the pass band effects in its equivalent low pass form without the carrier. So, only if you have to translate it to the carrier, you have to do a frequency translation with f c and it will go to the corresponding frequency representation. So, in the next lecture, we are going to look at the low pass equivalent representation of a system, and then we will continue to discuss the response of a band pass system when excited by a band pass signal with its equivalent low pass representation form. Thank you.